Hello everyone, welcome to Pre-Calc for today. This is going to be a video lesson on Unit 6, which is graphing tangent, cotangent, secant, and cosecant functions. So don't get too alarmed by seeing these trigonometric words back into our units. It's not going to be as awful as you think. We already have all of the prerequisites that we need to graph these functions and to interpret some of the behavior that these functions have. So don't panic, it's going to be okay. I just want to preface before we get too far into it and before I forget to mention that this lesson will have a few things that go along with it. So this is kind of a strange lesson because we're tacking it onto the end of Unit 6 because it has the same kind of asymptotic behavior as the other, as our rational functions that we were just dealing with. So if you look at the schedule, and you scroll down to what today is, which is February 28th. Don't mind my February 27th and my recording. Today we are doing lesson 6, and this video will be put right there once I get done with it. But if you look to the far right column, we have an assignment that goes along with it. So this assignment will be due the next class. So the next time that I see you, I want this assignment from you. It's not too awful, don't stress, but there's also a quiz that goes along with this assignment. So the quiz is due March 2nd at 11:59 p.m. Okay, so sorry, just adding that in there. So this quiz that I'm talking about, you will find it on Canvas. It is a take-home quiz. If you go to modules, right here, trigonometric functions with asymptotes. So this is a take-home quiz. You have 2 tries at it. Your score will be the average of the 2 tries, and it is due March 2nd at 11:59 p.m. and it is 10 points. So I just want to make sure you are well aware that you have a quiz that goes along with this lesson and assignment today. Okay, with that being said, let's jump in. So we're going to start off with graphing this tangent function. So f of x equals tangent of x. Now recall, tangent of x is sine of x over cosine of x. That's that. We have the ratio between sine of x and cosine of x. Well, because it's a ratio, we're going to have some asymptotes. Where will those be? At every single x value where cosine of x equals 0. So if you throw it back to semester 1, our cosine of x, well, that's our x to r, or our x to radius ratio, but in terms of the unit circle, we just call it our x values. So if you think about it, our x will be 0 here and here. So what are those angles? Remember what those angles are? This is pi halves, and this is 3 pi halves. And this will be between 0 and 2 pi. But we're talking about not restricting our domain. So if we're thinking about where for every x value at which cosine of x equals 0, well, that will be at pi halves plus how long it takes for us to get to the next one is pi. And then the next one will be pi and pi. So we introduce that n, where n is any integer. So at every x value of pi halves plus pi n, our cosine of x will be 0. So it says draw an asymptote at each of these x values on your graph. So if we scroll down, here's our graph. Let's make a scale for it. So I'm going to make every 4 boxes on our x scale be pi. So that's pi, and then 4 boxes over will be 2 pi, and then backwards we'll have negative pi and negative 2 pi. And then I'm also going to plot in here pi halves and 3 pi halves, because our zeros are where our x is 0, our cosine of x is 0, our asymptotes will be at every pi halves interval. Well, pi halves plus pi interval, sorry. So pi halves, 3 pi halves, then also negative pi halves, and negative 3 pi halves. If you are not following along with your own note packet, I highly suggest that you do. So with that being said, let's scroll back up. We drew the asymptotes at each of these x values on the graph. Check. Now it says tangent of x has a 0 at every x value for which its numerator, well, the numerator sine of x is equal to 0. So recall where the numerator, or sine of x, is equal to 0, it will be, in our unit circle, it's going to be 0 and pi. But in terms of general solutions, it will be every pi n interval. So at every pi, 2 pi, 3 pi, 4 pi, our sine of x will equal 0. So then it says mark each of these zeros with a point. Okay, so at 0, 0, okay, pi 0, 2 pi 0. These are just our zeros for our tangent function. All right, so we got that done. Let's see what's next. Okay, at this point, it says, now plot the graph on your calculator and choose Zoom 7 trig. So actually, pause this video, get your graphing calculator out, and graph y1 equals tangent of x on your calculator, and then go to your window or your zoom and hit Zoom 7, which will give you the trig zoom window, which is super handy for this. So after you do that, make sure you pause this video and actually do that. We're going to use that information to fill in the remainder of the curve. So then we'll also use set notation to fill in the blanks, and we're going to assume n is any integral notation, as we were up here as well. Okay, I hope you paused the video and actually graphed it. So here I'm going to open Desmos, and I'm going to graph this f of x equals tangent of x. Okay, so if you graphed it, looks something like this on your TI-84. I'm using Desmos, but doesn't matter. You will see that this is the behavior, this curvy behavior of our tangent function, okay? So if we go back and draw this in, bear with me, we draw this kind of thing in. Well, first let me evaluate this. If this is pi halves right here, this will be pi fourths. So if you think about the tangent of pi fourths, because the x's are our inputs and our y values will be our outputs, remember pi fourths is right here where the ordered pair is root 2 over 2, root 2 over 2 in our unit circle. So if you think about taking the sine over the cosine, the tangent of pi fourths will just be 1. So I'm going to actually plot that point if we pretend that that is 1. And then if we think about this negative pi fourths, well, negative pi fourths in our unit circle, well, that will be root 2 over 2, comma, negative root 2 over 2. So that tangent of negative pi fourths is negative 1. So I can plot that point as well, negative 1, and then I will kind of graph the curve in here. And those are asymptotes, so we're never reaching those. And then we can continue to do so at every interval. It's not perfect by any means. But we kind of get the idea. This is what our tangent function looks like. Okay, so then we want to fill in the rest of these given our graph and kind of our previous knowledge of the trig functions. Okay, so if we think about what the period of the tangent function is, we start here, if we start at 0, 0, the next time we get to 0, 0 will be, or not 0, 0, but x equals 0 will be pi. So our period equals pi. This is for f of x equals tangent of x. Now, looking at our asymptotes, we have an asymptote at pi halves n, and then we move pi units over at 3 pi halves. Or sorry, yes. So our asymptotes will be pi halves plus pi n. Those are our asymptotes. We have one at pi halves, sorry, not pi halves n, pi halves, and then 3 pi halves, and then we'll have another one over here, which is another pi units away. So our asymptotes are at pi halves plus pi n. Our zeros, well, that was where the sign of x equaled 0. So we recall that was at every pi n interval. Okay, so we can do our domain and range based on this information. X is an element of all real numbers such that, well, remember when we were doing our rational functions, we excluded any of our asymptotes. So we're going to say x is an element of all real numbers such that x does not equal pi halves plus pi n. Right? If we look at where our function exists, it exists at all x values except for the pi halves plus pi n asymptotes. Then our range, okay, well, look at this. Well, our graph will go all the way to negative infinity, all the way to positive infinity. Okay, so y is an element of all real numbers. All right, but it's never just that, right? We're going to be transforming these functions. So if I transformed these functions, well, let's make it something else. Instead of f of x, let's make it t of x, the transformed function of tangent of equals tangent, let's transform it, a tangent of bx. Recall, the way we found our period was we would take pi over b. Well, when we found the period for sine and cosine, we would take the 2 pi over b, right? The original period divided by this transformation. But our original period here is pi, so how we find the period of our transformed tangent function is pi over b. Then our asymptotes, well, if we think about that, instead of at every pi halves, if our period shrunk, then we will be at pi over 2b plus pi over b n. Just divide both of these original by b. Our zeros will be pi over b n. And then our domain will still correspond with our asymptotes, so it cannot be pi over 2b plus pi over b n. And then our range is not going to change. It's going to be all real numbers. Okay, remember that n is any integer value. So our asymptotes will be at pi halves, 3 pi halves, 5 pi halves, and so on. But until we transform it, and then it's whatever this b value is, then that kind of has a factor in it. Let's go back to Desmos and look at this. So I still have my tangent of x on Desmos, but look at this right here. So I have plotted this asymptote of pi halves plus pi n, and then this slider, notice my n over here, this slider between -3 and 3, you can see when our n changes to integer values, you can see that our asymptotes are at every pi halves plus pi n interval, which I thought was kind of neat. Okay, let's go back. We've graphed the tangent function. Let's go to cotangent. All right, since cotangent of x is cosine of x over sine of x, recall, it will have an asymptote at every x value for which sine of x equals 0, right? It's what would make the denominator 0, and the denominator in this case is sine of x. All right, so now we need to draw an asymptote at each of those values. Well, we already determined where the sine of x was 0. It was at every pi n. Okay, so let's go down and let's draw that in. We'll do the same scale factor. Every 4 boxes is going to be pi. If you want to change it up, you can, but your graph will look just a little different than mine. Okay, so drawing in those asymptotes. Well, if n equals 0, we will have an asymptote at the y-axis. And then pi, 2 pi, also negative pi, and negative 2 pi. There we go. All right. Now, we need to determine where our zeros of this function, cotangent of x, are. So g of x equals cotangent of x has a 0 at every x value for which its numerator, well, what's its numerator? It's cosine of x is equal to 0. Remember that happened at pi halves, and then our period is pi n, because we're talking about the zeros of cosine. Okay. Mark each of these zeros as with a point. Let's go down here. Okay, so this would be pi halves. So there we go. 3 pi halves, negative pi halves, negative 3 pi halves. And we'd also have them over here as well, right? Our function is not continuous, but it keeps going, right? Just because we have this little window of what we're looking at, it would keep going beyond that. Okay, we did that. Now, go to your calculator and type in y1 equals 1 over tangent of x. Recall that cotangent of x and tangent of x are reciprocals. So 1 over tangent of x is the equivalent of cotangent of x. And then choose your Zoom 7 window again. Use this information to fill in the remainder of the curve. Okay, I hope you paused and you did that. I'm going to open up my Desmos and I'm going to plot my cotangent curve. Did you see this kind of behavior on your graphing calculator? Make sure you typed in 1 over tangent of x. Notice it's kind of like, instead of tangent of x, right, tangent of x, we climbed. Now we're kind of like falling as our x values grow. We're decreasing. Kind of interesting to think about. So let's graph that. Well, I want to actually get 2 points to graph it in our first little interval. So let's think about pi fourths and let's think about 3 pi fourths. Cotangent of pi fourths. Well, recall that would be just the same as tangent of pi fourths, right? Because they're reciprocals. And tangent of pi fourths was 1, so cotangent of pi fourths will be 1. They're not always the same, but in that case they are. So graphing that point, pi fourths 1. And then let's think about cotangent of 3 pi fourths. What will that equal? Okay, well 3 pi fourths is over here. So the ordered pair there will be negative root 2 over 2, comma, root 2 over 2. So taking the cosine over the sine, we will get negative 1. Okay, so at this point right here, kind of covering up that 3 pi fourths. But see how we have that falling behavior, the decreasing instead of the increasing, like tangent? Okay, let's plot these graphs. try it again. That wasn't very good. Okay. There's one. Keep going. Keep going. Kind of went over the graph there, but all right. It gets repetitive, right? They're kind of repeating themselves. I'll just graph this part right here. All right, so that is what we call our cotangent graph. Not bad, huh? All right, now our goal is to fill in the following right here. Our period of cotangent is going to be the same as the period of tangent, right? Look at, we're at pi halves, and then we traveled pi units to get to the next one, okay? So our period is pi. Our asymptotes, where do our asymptotes exist? Well, at every pi n, where n is an integer. Our zeros, well, that was at pi halves plus our period, which is pi n. Our domain corresponds with our asymptotes, so we will be all real numbers such that we do not equal pi n. And then our range, well, we will be all real numbers. Not such that we are just all real numbers. All right, so I want you to think about what the transformed function of this would be. So you can transform this cotangent further, but all that we're focused on will be mostly this b value. We don't really even care about that a value, but you will see some that have an a value in your homework. But so your job is to think about what would happen when you transform this cotangent function, and then fill out the rest of these. All right, not too bad, right? Now let's go back to this Desmos, because I want to show you this, the asymptotes of this again. So I have plotted my asymptotes of every pi n, and then if I turn on my nice little slider, kind of geeking out about this, but you can see our asymptotes are at every pi n, right? We don't have function values there. Our cotangent function is converging to infinity or negative infinity around those asymptotes. Kind of cool. Okay. Two more. Not bad, not bad. All right, so the secant of x. H of x equals the secant of x. Well, recall the secant of x was 1 over cosine of x. So the cosine function will control the shape of the secant graph, right? Because they're kind of reciprocals. So let's draw in this cosine curve first. Okay, remember the cosine curve started, well, if we have, instead of having this be 1 this time, since we're drawing in the cosine curve, I'm going to have 4 units be 1. So it's just my preference. Okay, remember the cosine curve started high, and then we followed this up, down, like high, middle, low, middle, high pattern. And so our period of the cosine curve was 2 pi. So this will be pi and pi halves, 3 pi halves, and let's plot it the other way as well. So going backwards. So this will be negative 2 pi. This will be pi, negative pi, sorry. Negative pi halves and negative 3 pi halves. So we're going to try to draw this cosine curve in. That takes me a little bit. We're getting there. Okay, and we'll finish it up over here. Now we're going to determine the relationship. We're going to try to see the relationship between this cosine curve. Well, let's say this green is our cosine of x, y equals cosine of x. And then we'll graph the cosine curve in red, or the secant curve in red, I guess. Let's think about this. Secant will have asymptotes wherever cosine is equal to 0, right? Because secant is 1 over cosine. So secant will have asymptotes when cosine equals 0. If we go below, down here, and look at where cosine is 0, that's at pi halves, at 3 pi halves, right? You can see this is my 0 for cosine, right here, right here. So we'll have asymptotes at those values, negative pi halves and negative 3 pi halves. Now, also recall that cosine was restricted, right? That ratio of x to the radius was restricted between -1 and 1. We never had a cosine value that was larger or less than negative, or 1 and -1 respectively. So since secant is the reciprocal, its values will always be greater than or less than or equal to -1 and 1. Its values will be the reciprocals of numbers between -1 and 1. Let's explore what these are. Okay, think about this. Where will secant of x equal 1? Well, secant of x, let's do blue. Secant of x equals 1, which secant of x also equals 1 over cosine of x. And we get 1 from, like, you can get the reciprocal of 1. 1 is the same thing when you take the reciprocal of it, right? So the secant of x equaling 1 will have the same idea as when, or the same value as when cosine of x equals 1. Because of this, when you take the reciprocal of 1, it's still 1. Your secant of x will be 1 at the same spot that your cosine of x is 1. So that is right here at this 0, here at this 2 pi, and here at -2 pi. Right? So the secant of x will be 1 at the same spot as the cosine of x being 1, because when you take the reciprocal of 1, it's still 1. And then the same kind of idea about the reciprocal of -1. The reciprocal of -1 is still -1. So secant of x and cosine of x will share values at all of those red dots that I have currently. Okay, we plotted those ordered pairs, plotted those points as well. Now go to your graphing calculator. I know you still have it handy from before when you paused the video and graphed it. And go ahead and graph this secant of x. How you will do this is you're going to type in 1 over cosine of x, right? It's the reciprocal of cosine of x. And our calculators don't have secant of x as a function. You just take the reciprocal of cosine of x. Then choose zoom 7, and then use this information to fill in the remainder of the curve. So pause the video, and we will continue after you do that. Okay, secant of x, right there. Look at that. Here, if I plot in the cosine of x, also, I think that might be beneficial for us. Notice the cosine of x is the red one. Then our secant of x is the blue one. So notice our, like, it's kind of like parabolic. I know it's not, but this U shape that we get from this secant of x. So here, at this value of -1.3, we have a kind of relatively small y value as well, right? That 0.296. But here, when we take the reciprocal of that 1.3, or the output, I guess, we're growing. See how if you take the reciprocal of a value, you get larger? kind of interesting to look at. While we're here, let's turn on that asymptote. Okay, so our asymptotes were everywhere where cosine was 0, or the output of cosine was 0. So here at pi halves, and then if I turn on that slider, you can see everywhere where there's a cosine value, a functional output of cosine being 0, you can see that our secant of x follows that asymptotic behavior at those lines. So at pi halves, and then at 3 pi halves, 5 pi halves, any pi halves plus pi interval. Okay, back to the graph. Let's graph this thing. So we had the U shape. Try again. U shape, right there. So as our values for our cosine got super, super close to, our y values, our output values got super, super close to 0, thinking about taking the reciprocal of like 1/10 or 1/1000th, right? Think about taking the reciprocal of 1/1000. Well, that will grow to 1000. So the reciprocal would be growing. When you take a reciprocal of a super small value, it will actually become much, much larger. Okay. Ooh, did not do that right. That one's a little rough too, but we're getting there. We are getting there. It's really hard to graph properly on the device that I'm using. Maybe I'll get better at it over the years. Let's hope, right? But kind of like that. I need to redo this one over here. That one's pretty bad. Hopefully it gets better. Little better. A little better, not too great. But you get the idea, right? All right, now we got to fill out the period, asymptote, zeros, domain, and range of this function. The period of secant will have the same period as cosine. And do we recall what the period of cosine was? It was period equals 2 pi. So if you look, right, we start here. We don't get to that y value again until 2 pi units later. So then our asymptotes, well, it starts at pi halves. And then pi units later, we have another asymptote. So pi halves plus pi n. Our zeros, the zeros of this cosine function, so just the cosine function, or not the cosine function, sorry, the secant function, just the secant function, not the cosine function. Getting that cosine function out of there. Where do we hit 0? Where do we hit this x-axis? Nowhere, right? There's no zeros of this secant function. So, putting my cosine back in there, we don't have any zeros. No zeros, or null set, no solution. The domain, well, our asymptotes will also kind of determine what our domain is. X is an element of all real numbers such that x does not equal pi halves plus pi n. And then our range, this one's a little more interesting than the tangent and cotangent, right? Because we don't have all real numbers. Notice, what y values do we have? We kind of have to do inequalities for this range, right? We have to exclude all of these values. Okay, so those values would be from -1 to 1. So instead of excluding those when we write out the range, we're just going to write everything that we do want to include. So all real numbers that are greater than or equal to 1 or less than or equal to -1. That is where our function exists, right? It doesn't exist in between -1 and 1. It exists above 1, at 1, below 1, and at -1. And then you will be tasked with determining what happens when you transform this function. But that is kind of a homework inquiry as well. And you can play around with your graphic calculator to determine what happens, or open up Desmos and see what happens as well. One more. Oh my goodness, one more. Let's see. We can do this. The cosecant of x. So m of x equals the cosecant of x. Well, recall, cosecant of x was just the reciprocal of sine of x. So this sine function will control kind of the shape of this cosecant graph. So what we're going to do is we're going to graph in that that sine function. Remember, sine started at 0, 0. Then it went up to 1, so I'm going to let my 1 be 4 boxes up again, and my negative 1 be 4 boxes. That's not 4. 1, 2, 3, 4. 1. Maybe it was 4. Maybe I just can't count right now. And 1, 2, 3, 4. There we go. I don't know. All right. Anyway, remember we started at 0, 0, and then when we got to pi, we were back at the middle, and then 2 pi, we were back at that middle. And so we start middle, high, middle, low, middle, high. And it follows that periodic behavior. So we can just repeat. And so then this will be negative pi, negative 2 pi. This will be pi halves, 3 pi halves, and so on. Okay, let's draw this in here. Let's see if we can kind of get the sine curve down a little bit. I'm sure it takes you a lot shorter amount of time to graph this. Maybe my hand is just too shaky. I don't know. But you get the idea, right? That's our sine curve that we just love so much. Okay. We drew the lightest possible. I don't know if I can change the... Oh man, I can change. Wow. So cool. Anyway, you get the idea. So cosecant will have an asymptote wherever sine of x is equal to 0, right? If sine of x equals 0, then we'll have 0 in the denominator of our function, and we don't want that. So we're going to draw an asymptote wherever that was. Well, sine of x is equal to 0 at 0, or at x equals 0, at x equals pi, at x equals 2 pi, negative pi, and negative 2 pi. And it'll continue, right? It's not just this window, but at every pi interval, we'll have a 0 for our sine function, which means we'll have asymptotes at our cosecant function. Okay, same kind of idea as when we did secant. Since sine is between negative 1 and 1, then cosecant will be outside of negative 1 and 1, right? We'll have values that will be the reciprocals of numbers between negative 1 and 1. So think about where cosecant will be 1. Well, the same place that sine will be 1, because when you take the reciprocal of 1, it is still 1. So we'll plot all of those points. We'll have one at pi halves. Then we will have one at negative 3 pi halves. Or not negative 3 pi. Yes, negative 3 pi halves. Sorry. Okay, that messed me up a little bit, but I guess we're going to have one at negative 3 pi halves. Then where we have our negative 1, where our function value will be negative 1, will be at 3 pi halves, at negative pi halves, and so on. So you see where all of those red dots are, that's where our function's cosecant of x and sine of x actually have the same value. All right. We did this. Plot those points. Now okay, so now stop. You're going to pause this video, graph this cosecant of x. How you're going to do that is type 1 over sine of x and then choose zoom 7. You're going to use this information to fill in the remainder of the curve. So this is the last time you've paused the video, the 4th time that I have demanded for you to pause the video, so I hope you've actually done it, and you're going to graph this function on your calculator. All right. Now, opening my Desmos, cosecant, that's what I want to graph. Oh, I also plot in my sine of x here. Sine of x, so you can see this kind of relationship between the two. So here's our cosecant of x, and then we have, oh sorry, I have a dog barking, but we have asymptotes at every pi n, right? If you see, I plotted my pi n and put my slider in for n being integers, you'll see we have the secant of, or the cosecant of x, sorry, the cosecant of x has asymptotic behavior at every pi n interval. So let's go back to our graph. Let's graph this thing. It's those U's again, right? Kind of looks like U's, which are not fun to graph on this, so. Got something, right? Looks okay. I don't like that one. All right, look at that. So everywhere where you see the red is our m of x equals cosecant of x. That's our cosecant of x function. Isn't it just lovely? All right, let's go up and fill out our chart. The period of cosecant of x, well look, we were at pi halves and then we traveled 2 pi units to get to the next. So our period will be 2 pi. The asymptotes, what are the asymptotes of cosecant of x? Well, I wanted to write this in blue actually. The period is 2 pi. And our asymptotes occur at every pi n. So pi n. Our zeros, where does the cosecant function hit that x-axis? It doesn't, so no solution. We don't have any zeros. The domain will be all real numbers such that we are not those asymptotes, so we are not any pi n interval. And then our range. Y is an element of all real numbers such that. Same range, same idea as secant of x. We do not exist in between 1 and -1, right? Our function does not exist between 1 and -1, or -1 and 1. So how we write this is we just write everywhere where our function does exist, which is greater than or equal to 1 or less than or equal to -1, right? Greater than or equal to +1 or less than or equal to -1. We will have functional values. Okay, so then you will have the fun and exciting task of determining the transformed, like what happens when we transform the secant and cosecant function, and the tangent and cotangent function as well. So that is where your assignment 6 comes in, but for now, here are your 4 parent graphs of these tangent, cotangent, secant, and cosecant functions. We will have time for questions, so if you have questions, next class we'll have a little bit of time to go over that, and then you'll have your quiz, like we'll have class again before your quizzes due. So our next class will be March 2nd. Your quiz is due that night at 11:59 p.m. And you have this homework here, so I would love for you to have it done before the quiz. And I understand that you will have the quiz March 2nd. It's done, like you have to have the quiz done at 11:59 p.m. So if you get this homework to me by Friday, what would that be, March 4th? If you get this homework to me by Friday, I'll be fine with that as well. So that in case you're working on it right before you take the quiz, that kind of thing. This assignment 6, just at any point during the week before Friday, I would like this homework in so that I can get it graded and put into the gradebook for you. And with that being said, I think that's all that I wanted to tell you for today. I hope you have a lovely day, whether it's this Monday that you're watching this or Tuesday, Wednesday, so on. I hope you just have a fantastic day and this trig graphs unit puts you in a great mood and you're just ready to conquer the world after this, because that's how I feel, right? All right, so before I mumble too long, thank you for listening. Hope it wasn't too boring, kind of bringing back some of that entertaining trig stuff from last semester. Again, this is just tacked on to the end of Unit 6 because of the asymptotes, that kind of asymptotic behavior. And we wanted you to see the tangent, cotangent, secant, and cosecant graphs, because if you do continue your math career after this, which I hope you do, they're not going away. But have a good day. Bye.